Hello dear students, in today's class we will be discussing the sign convention for lenses. So similar to sign convention for mirrors, we have sign convention for lenses also. Okay, so let us see one by one what are the sign conventions. So all distances are measured from optical center. So in the case of mirror, the first sign convention says that all distances are measured from pole of the mirror. So in the case of lens, so all distances are measured from optical center of the lens. So you know what is optical center. So this point we call it as optical center. So from the figure, so whatever the this thing, so this is lens actually. So whether it may be convex or concave, so I'll consider this part as lens. So it may be convex or concave. So first one says that, so this will be the optical center, this point will be the optical center. So all distances are measured from optical center of the lens. So second point, distances measured from the optical center in the direction of the incident light are taken as positive. That means the incident light will be this side. Okay, so distances measured along the direction of incident ray is taken as positive. So third point, the distances measured from the optical center against the direction of incident light are taken as negative. That means if the distances measured are opposite to the direction of incident light, it is taken as negative. Clear? So fourth one, distances measured upward and perpendicular to the principal axis. That means the height measured above the principal axis is taken as positive. Fifth one says the height below the principal axis, height measured below the principal axis is taken as negative. So these are the five sign conventions we need to follow while solving the numericals. I will repeat it once again. So first one, all distances are measured from optical center of the lens. Second one, distances measured from the optical center in the direction of incident light are taken as positive. Third one, the distances measured from the optical center. The distances measured from the optical center against the direction of incident light are taken as negative. Fourth one, the distances measured upwards and perpendicular to the principal axis are taken as positive. The distances measured downward and perpendicular to the principal axis is taken as negative. Here fourth one is the distance measured upward and perpendicular to the principal axis is the height of the object or height of the image. In the fifth case also it may be height of the object or height of the image. Remember, height of the object will be always positive because we will consider object above the principal axis. In certain cases height of the image will be positive and in some cases height of the image will be negative. So in all virtual erect cases, if the image is erect, we will consider it as positive. If the image is real and inverted, we will consider it as negative. We will consider the height of the image as negative. So hope you are clear with the sign conventions in the case of lenses. So there are some important points we need to go through. So for solving problems, this important points will be helpful. So some important points. So in the first case, uh, a convex lens, when a real image is formed. In the case of convex lens, when real image is formed, the object, that is object distance u is always negative. In any case u will be always negative. So if the image is real, v is always positive in the case of convex lens. Why v is positive? So because the image formed will be right side of the lens. So distances measured right side of the lens will be taken as positive. Distances measured left side the lenses are taken as negative. So in a convex lens we always get real and inverted image right side. So only virtual and direct image will be left side. So that is why when the object when the image formed is real in the case of convex lens, u is always negative, v is always positive, and focal length in the case of convex lens is always positive. Okay, focal length in the case of convex lens is always positive. So second case, a convex lens when virtual image is formed. So when virtual image is formed, u is always negative, that is object distance is always negative. So in all the cases object distance is always negative. So v, that is the image distance is negative. So in the case of virtual image formed by convex lens, because in the convex lens, so between focus 1 and optical center, when we place the object, we will get the image on the same side of the lens. So if we are getting the image on the same side of the lens, that means image is left side. So if the image is left side, it is virtual and direct. So that is the reason why in the case of convex lens, when the image is virtual, that is virtual image, so v will be negative, that is image distance will be negative. So in the convex lens, focal length is always positive. So remember, focal length is always positive in convex lens, u is always negative in convex lens, and only in two cases v will be positive and v will be negative. So when the image is real and inverted, v is positive. When the image is virtual, v is negative. So hope you are clear with the sign conventions here. So we will move on to the next slide. So here the last case, that is concave lens. In case of concave lens, so in the case of concave lens, we have only two ray diagrams. One is from the infinity and second one is between infinity and pole. Only two cases we have. So what are the sign convention for two cases? I already said you, that is the object distance is always negative in all the cases. So object distance is always negative. So v is always negative, that is image distance is always negative in the concave lens, because image formed in the concave lens is always left side, that is on the same side as the object is placed. Okay, so f is always negative. Since it is concave lens, what we will have virtual focus. So whatever the focus will be, it will be also in the left side. Let me show you. So this is a concave lens. So when you send a ray, it will diverge like this. If you draw this ray backward, that is this will be the focus. So this, the rays appear to meet, we will have virtual focus. Since the distance is measured left side, so focal length will be negative. So that is why in the case of concave lens, so object distance, image distance as well as focal length is considered as negative. So it is easy to remember. In the case of concave lens, all the three cases will have negative. Okay, so hope you have understood all the three, A, B and C. So in the case of convex lens, let me repeat it once again. In the case of convex lens, so when the image is real, u is negative, v is positive, focal length is positive. When the image is virtual, u is negative, v is negative and focal length is positive. So in the concave lens, u, v and f are negative. Okay, let us go for the next concept, that is lens formula. So similar to mirror formula, we have lens formula. So mirror formula is 1 by f is equal to 1 by v plus 1 by u, whereas lens formula is 1 by f is equal to 1 by v minus 1 by u, where v is image distance, u is object distance, f is focal length. Okay, so 1 by f is equal to 1 by v minus 1 by u. So now we will move on to linear magnification produced by lenses. So in the case of mirror, the linear magnification is explained as the ratio of height of image to the ratio of height of the object. In the case of lens also it is same. The ratio of height of image to the height of the object is called its linear magnification. So or you can define it as the distance of image to the distance of object. So linear magnification will be equal to height of the image to the height of the object. Height of the image is taken as hi, height of the object is taken as ho. So m will be equal to hi divided by ho. Also m is equal to distance of image to the distance of object. So image distance is represented by letter v, object distance is represented by letter u, therefore m is equal to v by u. So from this equation and this equation we can write m is equal to hi divided by ho is equal to v by u. So in the case of lens, m is equal to hi, that is image height to the object height, which is equal to image distance to the object distance. So this is the magnification formula in the case of lens. In the case of mirror, only difference is m is equal to hi divided by ho is equal to minus v by u. In the case of lens, it is m is equal to hi divided by ho is equal to v by u. Okay, so okay, there is a note. So if magnitude m is greater than 1, if magnification is greater than 1, that means the image is magnified or enlarged. If the magnification is equal to 1, the size of the image is same as size of the object. If the magnification is less than 1, the image is diminished. Okay, this all I have explained in the mirror concept. The same holds good here also in the case of lens. So we will move on to the next topic, that is power of lens. So what is power of lens? So power of lens, so you might have heard about spectacles will have some power, so that is 0.5. so this is power. What is the power? What is that actually power of lens? So power of lens is a measure of degree of convergence or divergence of a light rays incident on it, or the ability of lens to bend the rays, to converge the rays or to diverge the rays. This ability of the lens we call it as power of lens. So what is power of lens? Power of lens is the measure of degree of convergence or divergence of light rays incident on it. Okay, so if this is a lens, so if the rays are coming from some point, so like if it at what exactly, at what point it converges or at what point it diverges. If it is diverging lens, the rays will be diverging. So this ability of lens to converge or diverge, so the measure of this convergence or divergence we call it as power of lens. So in other words, we can explain it is the ability of lens to bend the rays of light incident on it. So mathematically it is defined as the reciprocal of focal length in meters. The reciprocal of focal length in meters we call it as power of lens. So thus the power of lens will be equal to 1 divided by reciprocal, in the sense 1 by focal length in meters. So P is equal to, mathematically we can write it as P is equal to 1 divided by F in meters. However, if the focal length is given in centimeters, usually while solving problems the focal length will be given in terms of meters, centimeters. So if the focal length is given in terms of centimeters, so how to convert it into meters? So centi means 10 power minus 2. If we take it down, it will become 10 square. 10 square means 100. Okay, so P is equal to 1 divided by F whole divided by 100 in centimeters. Or you can, if you send this to numerator, if you send this 100 to numerator, so P will become 100 divided by F in centimeter. That is P is inversely related to F. If focal length increases, power of the lens decreases. If focal length decreases, power of lens increases. So I am saying you P is equal to 100 divided by F in centimeters. So what does it mean? Okay, let me explain. Like in few problems, the focal length is given as 5 centimeter. If the focal length is given as 5 centimeter, find its power. So power will be equal to 100 divided by 5. You can take it at 100 divided by 5 if it is given in centimeter. So 5 ones are 5 20s are. So power will be 20 meter inverse, that is diopter. So this is how you can solve the problems. If they give in centimeters, if they give in meters, you can take directly P is equal to 1 divided by 5 meters. So 1 by 5 is 0.2. so that is how you will get the answers. Hope you have understood power of lens. So I will repeat it once again. Power of lens is a measure of degree of convergence or divergence of a light rays incident on it, or you can call it as it is the ability of lens to bend the rays of light incident on it. Mathematically it is defined as the reciprocal of focal length in meters, we call it as power of lens. So thus power of lens will be equal to 1 by focal length of the lens in meters. So P is equal to 1 by F in meters. In few cases, if they give power of lens, in few cases if they give focal length in centimeters, then we can say power of lens will be equal to 100 divided by F in centimeter. So power of lens increases if focal length decreases, power of lens decreases if focal length increases. So it is inversely related to F. So next, unit of power of lens. So what is the SI unit of power of lens? The SI unit of power of lens is diopter. So it is denoted by the letter capital D. A lens is said to have power of 1 diopter. So when we call a lens having power of 1 diopter, if its focal length is 1 meter, if the focal length of the lens is 1 meter, then we say the power of the lens as 1 diopter. Hope you have understood. That is, we know P is equal to 1 by F, right? So P is equal to 1 by F. If focal length is 1 meter, then power will be 1 by 1 meter inverse. Meter inverse is nothing but diopter. So 1 diopter. So when we call power of lens as 1 diopter, if its focal length is 1 meter, then we say power of lens as 1 diopter. So as convex lens has positive focal length, so we know already convex lens will have positive focal length, concave lens will have negative focal length, because convex lens is having real focus, concave lens is having virtual focus. Since convex lens is having real focus, it will have focal length positive. Since concave lens is having virtual focus, it will have negative focal length. So as the convex lens has positive focal length, its power is said to be positive, and it is denoted by plus D. As concave lens has negative focal length, its power is said to be negative, and it is denoted by minus D. So in optical instruments, a number of lenses are combined. So in some optical instruments like camera or microscopes, some optical instruments, number of lenses are combined. So to increase magnification, so number of lenses will be combined. The sharpness of the image, to increase the magnification or sharpness of the image, the net power P of these lenses placed in contact with one another is the algebraic sum of individual powers. So in some cases the lenses will be combined, then the total power will be equal to algebraic sum of individual powers. So that is, net power P will be equal to P1 plus P2 plus P3 plus etc. if there are some more lenses in the combination. Okay, so this is about power of lens.